Hey, and welcome to the Calculus 1 exam for review. So if you're watching this, hopefully you know where to go, but if not, and somehow you got a link to this, just know that we are in the online math resources for students course that you could self-enroll into. And if you come down to calculus with analytical geometry, click on it. We'll take you to basically like the course page. And we're under test review materials. And version A is right there. This will be the version that we're working off. You can download it or you can look at it in here. I'd advise you not to look at it in here because it kind of makes it small. Like, see, it's going to stay in this one column and that's no bueno. So download it, have it up on your screen, and you can follow along. I am working on the answer key as we speak, as we move through this video. And once the video link has been sent, we will get it uploaded out here for everyone. So there we go. With that being said, I do have Decimos open. And I also have my TI-84 calculator open and ready to go, should I need it. All right. So let's jump out here. Also, another thing I'm going to bring up, just because I know that these are things that I generally have to look up sometimes. Integral shortcuts. That's going to be important for us. Let's just go to images. And here's the one I usually use. It's pretty good. So there's my image. And then the other one that I usually bring up is a trig chart. And it doesn't matter which one I use here. So let's just open this one. Oh, that's really small. Let's go back. Let's open this one. Hopefully it's a little bigger. Oh my gosh, it's not any bigger. I need something. Let's just open this in a new tab real quick. Yeah, that's pretty good size. We'll just keep that. There we go. That's better. I don't know why it's shrinking. All right, so there we go. So I'll just have these up here just in case I need them for a refresher because I can't remember everything. So I've got our exam review right here. So let's begin. So question 1, depending on what course you're in, I know if you are in my course with Mr. Armstrong that I have this one submitted by my students. So we got f double prime equal to sine theta plus cosine theta. And we also know that f of 0 is equal to 3. And f prime of 0 is equal to 4. They want us to find the original function. Okay. Or in applications, this would be like giving you the acceleration and they want you to take it back to the position function. Same situation here, just this is in terms of a function instead of, context with acceleration, velocity, and the position function. So I have our problem written down right here. So remember that we can take this and get it back to f double prime by using antiderivatives. So let's do that first. Sorry, not double prime. We can take f double prime. Hey, Tiffany. We can take f double prime and get it back just to f prime. So all we're going to use is antiderivatives. Tiffany, what's the antiderivative of sine?
I'm not in calculus.
Oh, okay. Well, this is a calculus review, just so you know. So feel free to stay and watch if you want, or you're free to go.
Okay. I'll say and watch just
Okay,
because I want to learn.
sure. All right. So the antiderivative of this sine is, and see, this is why I always bring up my integrals, because for integrals and trig functions, really the only difference is about like pluses and minuses and things like that. So sine is negative cosine. Okay, so we'll come back here. So we have negative cosine theta. And then the antiderivative of cosine, that's going to be sine theta. And then because we're doing the antiderivative, we're going to have a family of antiderivatives, which is going to add on plus c. So we want to figure out what the c is. And we can do that based on the information that they gave us. They told us that f prime, when you plug in 0 for theta, is equal to 4. So we're going to set up an equation and solve for c. So we know that it's 4 here because that's what f prime equals 4. And then we're going to have negative cosine of 0 plus sine of, I put theta back in there. That should be 0. Silly Mr. Armstrong. Plus c. So we just got to do a little bit of evaluating here. Cosine of 0 is actually 1. So this really is a negative 1. Because cosine of 0 is 1. 1 times a negative is negative 1. Sine of 0 is 0. So this goes away. And then we got a plus c. So all we got to do is solve that little equation right there for c, which means all we're going to do is to get rid of a negative 1, we're going to add 1. So c is equal to 5. Now we officially know what the first derivative looks like. F prime of 0 equals negative cosine theta plus sine theta plus 5. But that's not where we want to end. We want to know what is the original function. So we're going to take the antiderivative of this again. And that, gosh, me and my primes today, is going to get us back to the original function. So the antiderivative of cosine, well, we just talked about that. That is sine, is what we found right there. So this is going to be negative sine of theta. Antiderivative of sine is negative cosine. We talked about that. So that's going to turn into a minus cosine of theta. The antiderivative of a constant just puts a variable by it, a variable by it. So that'll be 5 theta. And then because we're working with a family of antiderivatives, this is going to be plus d. I don't want to use c again because I don't want to get you confused with the c that we used earlier. This is just another constant. So from there, we're going to solve for d because we have information given to us from the beginning that can help us. We know that f of 0 is equal to 3. So we're going to plug in and figure it out. So 3, because that's what f of theta is, equals negative sine of 0. Oops, putting a plus and it's really a minus, Mr. Armstrong, minus cosine of 0 plus 5 times 0 plus d. So we have 3 equals, We already said that sine of 0 is 0, so this guy goes away. We know that cosine of 0 is 1, so we got a -1. 5 times 0 is 0, so that goes away. And then we got plus d. And there we go. An easy equation to solve for d, because all we're going to do is add 1 to both sides, and d equals 4. So our final equation is negative sine of theta minus cosine of theta plus 5 theta plus 4. And there we go. That's number 1. Moving on. And so, there's only 15 questions total. Oh my gosh, I'm writing a 5. I'm supposed to write a 2. All right. Question number 2. So in this one, we are told that f of x is equal to 1 over x. And we want to estimate the area under the curve, okay, from 1 to 2 using 4 rectangles and right-handed endpoints. We're going to round to 4 decimal places, and then it also wants a picture. So I kind of do this backwards a little bit. So we're using right-handed endpoints, so that should be an R sub 4, not an L sub 4. That's okay. Easy fix. So we'll go back and fix that later. So that should be an R sub 4. And then I always start with the sketch. Okay, if I have to sketch, I'm going to start with the sketch. So we're going from x equal 1 to x equal 2. And we know that we're going to have 4 rectangles. Okay. All right. So I'm going to draw me a sketch. And okay, doesn't have to be a very big sketch. It's all going to lie in quadrant 1. So I'll put a 1. And I'm going to space that out a little bit more because everything's going to happen between 1 to 2. I like to try and make it look as even as possible. So that's 1, it's 2. So let's say 1 and let's say 2. Okay. So if we plug in, because I want to plug in along the way, 1 for x, well, that's 1 divided by 1, so that's 1. So it's kind of up here. And if we plug in 2 for x, well, that gives me a half. So it's right about here. So, and this is not actually a straight line. If you know what this thing looks like, it actually curves. And I advise you go into your calculator. If you're not sure what the curve looks like, go into your calculator and just graph it. 1 divided by x. Graph. See, there you go. See, it's a small little curve. Okay. Not very big at all. All right. So my window looks a little weird. Oh, that's why. Let me adjust my window so that looks a little bit normal because it looked a little off to me. That's because my y-axis is off. So I was like, because my y-axis was counting by 2s. There we go. This will be better. Yeah, now it looks like 1 at 1 and 2.5. There you go. Yeah, you should always double check that. If your window's off, a quick fix for that, go down to zoom standard, hit enter. And that was under zoom and zoom standard. Okay. So there you go. And you can do the same thing in Desmos. Go out here to Desmos. F of x equals 1 over x. And there you go. At 1, it's up at 1. At 2, it's at a half. Easy peasy. Okay. So we are coming back. We are doing right-handed endpoints, but before I do that, I need to figure out what is my delta x. In other words, how wide are my rectangles? So that formula is b minus a all over n. Our b represents the highest value. Our a represents the lowest value. Our n that's being divided by is the number of rectangles. So there's your a, b, and n. So we're going to have 2 minus 1 all over 4. 2 minus 1 is 1 all over 4. So there's our rectangle width. So in here, kind of splitting some things up because I know that these are going to be here now. This is going to be 3/2 because that's 1.5. This is going to be 5/4. And this is going to be 7/4. Okay, so to create my rectangles, I'm going by the right endpoints. So that's going to be the 5/4 when I draw a rectangle for my first guy, the 3/2 when I draw my second one. It'll be based off of the 7/4 and based off of the 2. So I'm going to start up here at the top since I'm doing right-handed endpoints. So I'm going to go up until I hit, and then I draw over and down. That's a right-handed endpoint. I'm going to go up from 7/4 until I hit, draw over and down. So 3/2, I'm going to go up until I hit, draw over and down. And from the 5/4, I'm going to go up until I hit, draw over and down. That's what a right-handed endpoint looks like for our function with 4 rectangles. So that's part B right there. There's your sketch. Now for part A, to figure this out, we run the formula, which looks like this. So our formula is 4. We start at 1. And we're taking f of x of I times delta x. Remember, this is what we call the Riemann sum. So what that looks like then, remember that we could factor out the delta x because it's just a common factor for every single one of these. So what we can do is our delta x is 1/4. We'll put that in front of a bracket. And then all we need to do, this sigma means to add. We're just going to add up all the y values. So I need to know the y value for my right endpoints. So I need to know f of 5/4 plus f of 3/2 plus f of 7/4 plus f of 2. That's what we have to figure out. Just get these Y values. And how do I get these Y values? You just plug in. What's cool is whenever you take 1 divided by a fraction, all that's going to do is flip it because it's like a reciprocal. So an example over here. If I want f of 5/4, that's going to equal 1 over 5/4. What I just said is whenever you're taking a number divided by a fraction, we don't really divide by fractions, we multiply by their reciprocal. So all that really happens when you take 1 divided by a fraction is flip it. Just like what you had to do sometimes when you did the integral using the integral power rule. Sometimes we just flip the fraction. So f of 5/4 is equal to 4/5. So I'm going to use that little fact real quick to my advantage. So this is 4/5 plus, well, that's a fraction, so that'll just get flipped to 2/3 plus, that's just a fraction, so that'll get flipped to 4/7 plus, we already know what f of 2 was. We said that that was a half. So all I need to do is go to my handy dandy calculator, add all these fractions up and multiply by 1/4. The best part is they said that we can round this to 4 decimals, so we don't need the exact answer. So I'm just going into my handy dandy hand calculator that I have here. I'm not going to put this up on the screen. You guys can put this into your calculator and add it all up. You know how to do that. So putting it in 4/5 plus 2/3 plus 4/7 plus 1/2. And I got in my calculator 0.6345238095. Oh, some other things that I've kind of talked with my students about. Whenever you were evaluating, say you don't remember that trick, you can do it in your calculator real quick. Notice we have our function here. If I hit second quit and come out here to my calculate screen, I can go to variable, scroll over to Y bars and use my function. So I got function here, click enter again because it's in Y1, put the parenthesis, and your first one was 5/4. Hey, there it is. But of course I had a fraction. So if you just turn that into a fraction, hit math, and we want fraction, enter. Hey, 4/5, just like what I said. Okay. Or if you wanted to kick it out like a fraction, hit vars, go to Y vars, hit function, hit enter, put it in as a fraction, alpha. Oops, no alpha yet. Now alpha Y equals, we can put it in as a fraction, 5/4. Scroll out to the side. There's our fraction answer. You could do the same thing in decimals. Just come over in here. You got your function in. All you got to do is tell it where to evaluate. F of 5/4. And if you want the fraction, just hit the little fraction key over here. Boom, 4/5. There you go. Quick evaluating. You don't have to do it by hand. That's just silly when you can double check yourself. Okay. So from my calculator, after adding all this up and multiplying by 1/4, this is what we get, but we're going to round to 4 decimal places. So that will be 0.6345. There's our answer to part A. So I kind of do it backwards a little bit. I like to get the sketch so that way I can kind of see my numbers that I need. And then I do some plug and chug. All right. Question 3. Okay, so question 3 is about an oil leak from a tank at a rate of liters per hour. Okay. The rate decreased as time passed. The values of the rate at 2-hour time intervals are shown in the table. Find the upper and lower estimates for the total amount of oil leaked from the tank over the interval 0, 10. Use 5 equal sub intervals. Okay. So that just means 5 rectangles. We don't need to draw a picture of this, but if you want to draw a picture, you can. Your 5 equal sub intervals are pretty easy to see. It's going to be from 0 to 2. There's 1, 2 to 4, which is 2, 4 to 6, which is 3, 6 to 8, which is 4, and 8 to 10, which is our 5th one. Okay. You can't, and when they talk about upper and lower estimates, so all they're asking us to do is the right-handed and the left-handed endpoints. Okay, that's really what they're after. So let's start working through this. Okay. So I don't know which one is the lower or the upper. So I'm just going to do the left-handed endpoint first, and then I'll do the right-handed endpoint. And then I'll be able to know which one is the lower and which one is the upper to plug in. So I'm not going to do this as a part A and part B real quick. I'm going to do this with what I need to figure out. Okay. And then put my answers where they go. So the first thing we need is delta X. Okay. So they tell us our upper and lower bound. It's right here. This is the interval 0 to 10. 0 is A, 10 is our B. So in my formula B minus A all over N, I have 10 minus 0 all over our N is how many rectangles? Well, that's the same thing as the subintervals. That's 5. So I wrote this down for us. So our B was 10, our A was 0, our N was 5. So that leads us to 10 over 5, which is 2. That's how wide our rectangles are. So now I'm going to do L sub 5 and figure that out. The left-handed endpoints with 5 intervals. So my delta X is 2. I just need to figure out what are all my Y values. Now, the left-handed endpoints, they will start with 0 and work all the way out to 8. So these are all the values I need to find the Y values for, which is great because the Y values are right there. So let me show you in words or written out what we just talked about. So what we need is, let's make sure I get the variable right. So this is T of H. Okay. We need T of 0 plus T of 2 plus T of 4 plus T of 6 plus T of 8. Because these are all the left-handed endpoints. So what we're really looking at here is let's get their Y values. So their Y values for T of 0 is 8.9 plus 7.9 plus 6.9 plus 6.2 plus 5.7. Okay. So that's what it looks like. And again, I'm gonna go to my handy dandy calculator and let it do its job. Okay. So we go out to our calculator, we're gonna take 8.9 plus 7.9 plus 6.9 plus 6.2 plus 5.7. That's, so this whole piece inside the bracket adds up to 35.6. Multiply that by 2. So 71.2 liters. Now I do want to go back and I want to make sure my answer makes sense. Or in other words, I want to make sure that this sounds right. So we're leaking at these rates, and this has been over 2 hours, so 10 hours. I think that's reasonable. So these are in hours and I'm leaking by liters per hour. Yeah, things are matching up. So there's one of our estimates. Now, is that the lower or the upper? I don't know yet. We need to experiment a little bit more. So let's get the right-handed estimate. So the right-handed numbers or the right-handed endpoints will be from 2 on up to 10. So the width doesn't change. It's still 2. That's our delta X. And so now we want T of 2 plus T of 4 plus T of 6 plus T of 8 plus T of 10. Good thing is we already know most of these answers. The only new one we need is what happens at T of 10, which is 5.3. So we really are looking at this. This is what I just described in words. Plugging in, like I said, we already know these answers. T of 10 was 5.3. Let me double check that, make sure. Okay. So I'm just going to grab numbers from what we did before. So starting from 7.9 on through to the 5.7, and then I'll add 5.3. So, oh gosh, I almost started with the 0 one. Bad, Mr. Armstrong. So 7.9 plus 6.9 plus 6.2 plus 5.7 plus 5.3. So again, going to my handy dandy calculator, doing some adding and subtracting, or not subtracting, just adding. 7.9 plus 6.9 plus 6.2 plus 5.7 plus 5.3. So all of this adds up to 32. Multiply that by 2. So we get 64 liters. And now comparing my answers, I know exactly what is what. So our lower estimate is the right-handed endpoints of 64 liters. Our upper estimate is the left-handed endpoints at 71.2 liters. And there we go. So I couldn't make these judgment calls until after I did a little bit of math. Okay. Because normally it kind of looks like when we were in class, if you had me, or probably with your professor, it looked like the left-handed endpoint was always the underestimate and the right-handed endpoint was always the overestimate. But not always true. Okay. All right. Actually, I had that reversed. It looked like the left-handed was always the, oh, it kind of did match. Okay. Rule of thumb, just in general, always make sure, you crunch your numbers and then you'll know. Because it's not always true. That the left is whatever and the right is whatever. It could flip. So moving on, let's get to question 4. Enough of my rambling. So question 4. So in this, we want to find right endpoint answers, left endpoint answers, midpoint answers. We're using 5 sub intervals. So if you notice, we're counting by ones everywhere. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, we got 5 sub intervals. So real quick, let's figure out what's going on. So we're basically doing kind of the same thing that we did right up. I mean, basically kind of like right up here, number 2 and number 3, but they just tried to give it to us integral style. That's all they did. They gave it to us integral style. So this 0 down here is the A, the 10 up here is the B, and the 5 is our N. So delta X is equal to our B, which is 10, minus 0, which is A, all divided by 5, because that was our N. So we know that we're going to have the same situation as a moment ago. Our intervals should be a length of 2. So that means my rectangles are going to span from 0 to 2 somehow. Okay. And then from 2 out to 4, there'll be a rectangle. So you can see that makes doing left endpoints, right endpoints, and midpoints easy, because the midpoint will be all the odd number intervals, or sorry, not intervals, but all the odd number tick marks. Our left endpoints will be all the evens starting at 0 up to 8. And our right-handed endpoints will be all the evens starting from 2 up to 10. And our midpoints, as I said a moment ago, they'll be the odd numbers, 1, 3, 5, 7, 9. Okay. So let's start doing some math. So I'm going to do the left, then I will do the right, and then I will do the midpoint. Okay. So as I said a moment ago, we need to figure out what is it f? Is that the function? Yeah, f of x. F of 0, because I said the left-handed endpoints will start at 0 and go up to 8. So we need f of 0, f of 2, f of 4, f of 6, f of 8. So let's go to our graph and get our answers. So f of 0 is down here at a -1. So f of 0 is a -1, plus f of 2. 2 is also down here at a -1, plus f of 4. So 4 is right here. It's up at a +1. Plus f of 6. Here's 6. It's up at a +3. Plus f of 8. 8's right here. It's down at a -1. So here's what we just found out. So these are all the y value answers. So all we got to do is some simple adding and then multiply by 2. So -1 plus -1 plus 1 plus 3 plus -1. And that answer, this all becomes 1. 1 times 2 is 2. So there's our left-handed endpoints. So I kind of do this out of order. So we actually know the answer to part B first. The answer is 2. Now I'm going to do the right-handed endpoints. So I'm going to do part A. So R5. So again, this time it's going to be 2 again. And then we want f of all the even numbers starting at 2 out to 10. So f of 2 plus f of 4 plus f of 6 plus f of 8 plus f of 10. So let's get our Y values. So f of 2, we already know, it's -1. F of 4, we already know, it was -1. Or sorry, it was +1. Oh, Mr. Armstrong, almost messing up. Was +1. F of 6, we already know, that was a +3. F of 8, we already know, that was a -1. Plus f of 10 is the one we don't know, and that's actually at 0. So here's what we found out. Here's all the Y values. So we do some quick adding and then adding and subtracting technically this time. And then we'll multiply by 2. So this all adds up to 2. 2 times 2, 4. There's the answer to part A. So now all we're going to do is the end, or excuse me, the endpoints, Mr. Armstrong, the midpoints. So part C, we want M5. So we already talked about this. This is going to be 2 times the odd numbers. So f of 1 plus f of 3 plus f of 5 plus f of 7 plus f of 9. So let's go look up these answers. So f of 1 is up at 2 plus f of 3 is at 0 plus f of 5 is up at 2 plus f of 7, which is right here, is up at 1 plus f of 9, which is right here, it's down at -2. So there's all the Y values again. So let's do some adding, subtracting, and multiplying. 2 plus 0 plus 2 plus 1 plus -2. So this all adds up to 3. 3 times 2 is 6. And there you go. That's it. That's all you had to do. All right, number 5. Number 5. Let's see what we got in store. So number 5, we want to know what is wrong with this. It's a quick multiple choice. So they did some stuff here and they actually got an answer. Okay. And we are asking, what is wrong with this? So it says graphing calculator recommended. Okay. So let's take the graphing calculator recommendation here and let's go take a look at this, because a lot of these answers are saying something about not continuous. So maybe we should go and check and see if this is continuous from pi to 3 pi. Okay. So we're going to put 4 secant theta tangent theta in the calculator, and we're going to see what happens. Because if it's not continuous between these numbers, then we have to choose one of these not continuous answers. Okay. So let's go find out some information. So let's delete this out of here. 4 secant x tangent x. Oh, so we do have like asymptotes and things like that. So the question is, what is this asymptote that's right here? Or even down here? Okay. So let's think about this interval real quick. We are going from pi over 3 to pi. So let's see what those numbers are. So pi, 3.14. Okay, good. And pi divided by 3. So our search is between 1 and 3. So here's 1 right here. And 3 is right here. See? 3. Close enough. So here's pi. Oh, so we know it's okay at pi. So that's not a problem. But what about at pi over 3? That's the question. So if this is 1, pi over 3 is somewhere around in here, like really close to 1. And I don't think that's going to be the problem. No, I don't think that's going to be the problem because right here is 1 and we're going past that and we're getting, these two lines are getting closer and closer together at some other number. So I don't think it's pi over 3 that's the problem, but there's definitely some asymptote in here, probably around, maybe 1.5. So looking at this problem, then we definitely know they couldn't have got this answer because it's not continuous. In order for this to work, the second part of the fundamental theorem of calculus, you got to be continuous on your interval. And we know it's not. So we just need something that says that. So 4 tangent theta is not continuous. Well, no, that doesn't matter. Okay. Because we're not dealing with 4 tangent theta. Okay. So 4 secant is not continuous at, well, again, that doesn't matter because we're not dealing with 4 secant theta. The lower limit does not, well, that doesn't make it, that's just junk. 4 secant theta tangent. Hey, we're working with this. Not continuous on the interval. Oh, I agree. So hey, right here, it's D. There's your answer. Okay. And again, that D answer of 4 secant theta tangent theta is not continuous on pi over 3 pi. Remember, we saw that there is some asymptote. Around like 1.5. We saw that. There's some asymptote around that number. Okay. All right, so nope, never mind. Number 6. So number 6 says let g of x equal the integral from 0 to x of f of t dt, where f is a function whose graph is shown. Answer parts A through D. So local max, local min, absolute max, intervals of increasing. Hey, this is a lot like what we did in exam 3 when we explored graphs. Okay. So give me 1 second just to take some notes of what our answers were after. So A is all about a local max, B is all about a local min, C is all about an absolute max. And D is all about when are we increasing? Okay. On the intervals. So one thing you need to understand, this graph is of f of t. F of t is in my integral right here. So if you remember from your teachings, this function that is in here represents the derivative. The g of x out here if we evaluated the integral, would be the original function. So this really is an exam 3 type question, because we are asking you in here to look at a derivative graph and tell us information about the original. This is an exam 3 question. This is a derivative graph because f of t is the derivative. When you take the integral of a derivative, you get back to the original. Okay. So since this is a derivative graph, we want to look at, in order to find possible max and mins, the zeros and where it does not exist. Well, if you look at this, excuse me, this graph exists everywhere. So we don't have to worry about the does not exist case. But we do have zeros. Where are those zeros? And it looks like we're counting by 2, 4, 6. We're counting by twos. Okay, so we have a 0 at 0. So there's one of our zeros. We have a 0 at 2, 4 is a 0. 8, 10, 12 is a 0. 16, 18, 20 is a 0. 24, 26, 28 is a 0. And out here at 32, 34, 36 is a 0. Now, what we have just found and talked about is that these are all the possible max and mins. These are all possible max slash mins. Again, we didn't have to worry about the does not exist case because, well, it's continuous everywhere on that interval. So I'm going to create my little number line. We're going to start at 0, and then we've got a 4, then we've got a 12, got a 20, a 28, and a 36. So these are all the intervals we're going to check. We're going to check each one of these little separate intervals. So let's start taking a look at what is the derivative doing, or in our case, it's f, and see what that's going to tell us about g, which is the original function. I think, are we in x's? So it's f of t, which converts to x. So weird, but that's fine. So remember, this is the derivative, even though it says f of t, it's the derivative. This is the original. So if we look right here at our intervals, so is there anything before 0? No, which leads me to believe that this 0 is most likely an endpoint. Okay. This 0 is an endpoint. So we're not going to worry about that for part A and B. It's an endpoint. Okay. Local maxes and mins cannot be endpoints. And you can say the same thing over here at 36. There's nothing beyond 36. So we're not going to worry about beyond that, but this will allow us to think of 36 as an endpoint. Okay. So let's look at everything else. So the interval from 0 to 4, well, my graph is above the x-axis. So that means the derivative is being positive. The interval from 4 to 12, my graph is below the x-axis. So that means my derivative is negative. And then it goes to positive for the next interval from 12 to 20. We're back to negative for 20 to 28 because we're below the x-axis for the derivative. And then we're back up to a positive. for the last interval from 28 to 36. So here's what we just talked about. These two intervals don't exist. There's no information. Here's what we know about our derivative graph. So since the derivative is positive, what does that mean about G? That means it's increasing. Since the derivative is negative, we're decreasing. Since the derivative is positive, we're increasing, then decreasing, and then increasing. And now we know all about our local maxes and mins. Okay. So here, when the graph goes increasing to decreasing, this guy is a max. When the graph goes decreasing to increasing, the 12 will be a min. When the graph goes increasing to decreasing, that means 20 will be a max. And the graph goes from decreasing to increasing, that means the 28 will be a min. So there's parts A and B. All right, so now for part C. Part C wants to know what is the absolute max? Well, think about this now. This is where the integral is really going to come into play on this. Because part D, we don't need the integral. We are actually already have the answer for part D. So let's go ahead and do part D and then we'll do part C real quick. Part D just says, when is it increasing? Well, we already know that. When are we increasing? So we're going up from 0 to 4. Okay. We're decreasing. We're increasing from 12 to 20. So comma, 12 to 20. And we're going down. We're increasing from 28 to 36. So there's the increasing answer. So the question is, where is there an absolute max? Well, like I said, this comes involved with the integral. Remember, the integral is all about the area under the curve. And when you find that area under the curve, you can relate it to distance traveled on the original function. So this area right here is a small area. That means to get from 0 to 8 in the original function, you didn't travel very far. Okay, or sorry, not 8 to 4. From 0 to 4, that's a small area. It means you didn't travel very far. And because it's positive, that means we didn't travel very far in the positive direction. So we know that 4, which was listed as one of our local maximums, this one is not going to cut it because this area is smaller compared to the other ones. So if you keep that in mind, this area is medium sized compared to those. So when we go from, let's see here, this was 12 to 20, we definitely traveled further than the 0 to the 4, but we didn't travel as far as what happened here. So this distance right in here, this area under the curve means that we traveled a great distance from 20, what is this? 28 to 36. So that means this endpoint of 36 is going to be up at a higher point because this area is huge. It is larger than the other two positive areas. Thus, we now know that 36 has to be the absolute maximum because you have traveled a larger distance here because the area is huge. All right, so there's the answer to part C. It is 36 because this area in here was the largest out of the 0 to 4, the 12 to 20, and the 28 to 36. It was the largest. And there you go. So our endpoint of 36 was actually an absolute max. Okay. Now, from there, let's move on to question 7. Question 7. So again, and I think this is the last one where we're actually going to sketch a curve and do a Riemann sum. Yeah, we're going to get into the integral stuff. So this is the last kind of like long one that you might have to do. So part A, I want you to find the Riemann sum for f of x equal to 2x minus 1 from -6 to 4, 5 equal subintervals. And we're going to take a sample to be the right-handed endpoints. Okay, so we're doing an R sub 5 for part A. That's what we want to know. For part B, we want to know, or I want to know, do you really know what a Riemann sum represents? Or is, I should say. What is it? And then I'm going to start with part C, which is the sketch of the curve. Okay, because I think, I like to, when I work with my Riemann sums, if I have to draw a sketch, that's usually what I start with. So I'm just trying to figure out how large my graph has to be. Give me just a moment. Okay, I got an idea now. One, two, three, 4, 5, 6, 7, 1, 6, 7. So my x-axis, I'm going to count by ones. My y-axis, I'm going to count by twos. So we know that, just writing some information down. Oops. Two x minus 1. We are going from -6 . Okay. So here's what we know. Sorry that took me just a moment. So again, I made my graph counting by ones, counting by twos on the y. This is what we know. This is all that we're trying to find out. Okay. So I'm going to start getting my graph real quick. So I'm going to plug in -6. That will give me -12 minus 1, -13. So at -6, 2, 1, 2, 3, 4, 5, 6. So I'm going to be down here. Let's see here. 2, 4, 6, 8, 10, 12. Right between. As best as I can. We're right there. And then let's see here. Let's do another kind of in-betweener here. So maybe let's do something at 4. So let's plug in 4. -4. -4 times 2 is -8. -1 is -9. So 2, 4, 6, 8, 10. So -9 right in here. Go out to 4. So right there. 2, 4, 6, 8. Yeah, close enough. So let's do a -2 real quick. So a -2 is -4 minus -5. So we know that this is going to be, oh gosh, that could be a little bit lower. We know that this is going to be linear in nature because it's a line. If you plug in 0, you get -1. If we plug in, let's do 2, so that's 4, so that's a +3. And then if I plug in 4, 4 times 2 is 8, 8 minus 1 is 7. 2, 4, 6, 8, 7. Right about there. So I did a pretty good job of trying to keep it straight. So here's what our graph looks like. Best as possible. You know, my dots are not exactly the greatest. Yeah, something along those lines right there. There's our line. Okay. Now we are doing right-handed endpoints and we are doing 5 subintervals. So I know I'm going to need to figure out delta X. So here is our A, here is our B. We know that N is equal to 5. So 4 minus a -6 all over 5. So again, hey, look at that, 10 over 5. We love that number too. So we know our intervals are 2. Hey, cool. Look, I kind of actually already did my intervals of 2. So we just got to make right-handed endpoints. So that means we're going to be working at -4, -2, 0, 2, and 4. That's where all of our rectangles are going to be based on. So I'm going to extend until I hit, draw across, and down. Extend until I hit, draw across, extend until I hit, draw across, extend until I hit, we draw across, and we extend until we hit, and we draw across. And there we go. Oh, that's a big box right there. I don't know why I was doing that. Need to extend it down. There we go. That's much better. So there is part C. There's what the picture looks like. And so now let's go ahead and find the rest of our Riemann sum. So we've done plenty of these by now. So we know that the 2 is going to be on the outside. And we need all of our right endpoints. So we need to know what is f of -4 plus f of -2 plus f of 0 plus f of 2 plus f of 4. And I actually already gave you all those answers. When we plugged -4 in, remember we got -9. Plus, when we plugged -2 in, remember we got -5. 0 gave us a -1. 2 gave us a +3. And 4 gave us the 7. So we just go right into our handy dandy calculator and calculate that up. -9 plus -5 plus -1 plus 3 plus 7. And this all adds up to -5. And we multiply that by 2. There's part A. So last but not least, the question is, what does this Riemann sum here really represent? And the picture gives us the information. The Riemann sum, remember, all you're doing in here is we're adding up all the areas of these squares. Because if I take the 2 back through, remember that this is the width. Sorry, and I said squares of rectangles. This is the width of the rectangle. This is the height of that rectangle. So these are all just the areas of my 5 rectangles. That's what the Riemann sum represents. It is the addition of all of the rectangles area under my curve. Addition, or you can call it summation, of all the area of the rectangles under the curve. There you go. That's really what a Riemann sum is. You're summing up all the areas of the rectangles that lay under your line or curve. Yeah, pretty easy. Nothing crazy there. That's really what the Riemann sum is. You're adding up all my little rectangle areas, and there were 5 of them. All right. So I'm going to give you a break on Riemann sums. Now it's all about integrals. Okay. So we are on now to question 8. And if you have class with me, you're going to turn in question 8. And maybe for other professors too. So we want to evaluate this integral from 1 to 6 of 2x plus 5e to the x plus 1 over x dx. And we want to be exact, no decimals. All right. So using integral properties, I can separate these out, and anything that's a constant, I can put in front of the integral. So if I use some properties, this is really what we're looking at. The 2 in front of the integral from 1 to 6 of x dx. That's my first guy. So this is just going to be a power rule that we use. Remember, the power rule for integrals is 1 over n plus 1, x to the n plus 1. And then we're going to add, I'm going to move the 5 out front of the integral from 1 to 6 of e to the x dx. And we know that the integral of e to the x is e to the x. So we'll keep that in mind. Plus the integral of 1 to 6 of 1 over x dx. Now, I'm not going to call this x to the negative 1 and use the power rule. Because remember, the power rule we just said looks like this. If I plug in negative 1, that's going to give me 1 over 0 here and x to the 0. This is the problem. Can't have that. So this is why I leave it as 1 over x, because we know the shortcut to this is really just ln absolute value of x. So this is not a power rule in disguise. This is ln in disguise. So there's what my integral really looks like using my properties of pulling constants out, and I can separate addition of different functions. So all that good stuff. So let's go in and let's do the evaluating. So this is just a power rule where the power is 1. So I'm going to have 2 times 1 plus 1 is 2. So that's a half. And then 1 plus 1 is 2. So that's x to the second. So this piece right here really just becomes x squared. Plus 5 times e to the x becomes e to the x. And there's no simplifying there. So we'll have plus 5 e to the x. Plus 1 over x, we just said that's ln of x. In absolute values. And because we are dealing with a definite integral, we don't worry about the plus c. And there's no reducing here. And we're going to evaluate this entire integral here from 1 to 6. So in order to evaluate this, we're just going to plug in what we know. So we're going to plug in the 6 first. So we got 6 squared plus 5 times e to the 6 plus ln of 6. And we're going to subtract that from plugging in the 1. And it's going to be in its own little bracket. So we'll have 1 squared plus 5 e to the 1 plus ln of 1. So now it's just all about reducing and combining and simplifying anything that we can. So 6 squared is 36 plus, there's nothing you can do here. That's a decimal answer. So that's just, and we don't want decimals. So that's just 5e to the 6. There's nothing you can do here. Again, you plug into your calculator, this is just a decimal answer. So that's ln of 6. Now remember, the minus is going to go through to all of these. So let's do some simplifying in here as best we can. And then remember that we're just going to change the signs to the opposites. So 1 squared is 1. Opposite of a positive is a negative. So we got minus 1. Again, nothing you can do here. E to the first is just a number. And this is going to be a decimal, but we want exact. So this is a positive 5e to the first, but the opposite of that is a negative 5e to the first. ln of 1, we can figure that out. That's 0. So that just goes away. So this is what we have now. So we just need to combine like terms. And all that's getting together is the 36 and the negative 1. So that'll give us 35 plus 5e to the 6. I'm going to go ahead and put the other 5e to the first by it because I like my e's to be together. And they're going to end it with a plus ln of 6. There, my friends, is the exact answer. Nothing crazy. All right. Number 9. Number 9 is a nice little multiple choice. So we want you to rewrite this using nothing but the exponents. So one of these is the answer. All right, so let me write this down. So we got the integral from 1 to 4, and you're not going to evaluate this. Of 4 plus x squared all over the square root of x dx. So because we have addition and subtraction in the numerator, really it's just addition, we could separate these into 2 fractions. And also we know that the square root of x is really just x to the 1/2 power. So taking those 2 things in mind, I can separate these to 4 over x to the 1/2 plus x squared over x to the 1/2. And of course, this would probably be in parentheses, dx. And now remember that we can move things to the numerator in here because all we're going to do is subtract down. Well, since there's nothing up here because there's a 4, but since there's no x up here, how do I move this x up? Remember, you can just make it its opposite power, or the opposite of the sign on the power. Because anytime you want to move a variable to the numerator, you just change the sign of the power. So the opposite of a positive 1/2 is a negative 1/2. So we got the integral from 1 to 4 of 4x to the negative 1/2. And that moves it up into the numerator. plus, since I have two x's here, we can just subtract the powers. 2 minus a half gives me x to the 3 halves. Dx. And that's what they're looking for. We just got to find the multiple choice answer for that. So the integral from 1 to 4 of 4x to the negative 1 half plus x to the 3 halves. So come in here. Those are all positive halves. So wait, here we go. Here's the only negative one. So that's easy. Right there, that's the one that we made. So the answer is B. Okay. Number 10. Let me write this down. So the integral from 0 to 18 of x over square root of 9 plus 4x dx. So it says use u substitution as if you were evaluating. How would the integral look once u substitution is performed? Do not evaluate. So cool, we're not evaluating. We just want to know, what does this look like when we have u in there instead of x? So our answer should not contain any x's. It should all be in terms of u. So that's what they want. Okay. So we know we're going to use u substitution. So if I look at this, thinking about it as a composition, my gut is telling me to work with this down here. So let's do that. I'm going to let u equal 9 plus 4x. So if I take the derivative of this, then du is equal to 4 dx. Okay. So if I solve for dx, dx is equal to 1/4 du, because you just divide both sides by 4, and that's 1/4 du. All right. Now, remember that these numbers right here are based on x. In my new integral, I need numbers based on u. That's why we have this right here. We're going to take the 0 and the 18, and we're going to plug it in here to figure out, well, what are the u limits? Because these are x limits. We need u limits. So to get my first u limit, I'm going to take 9 plus 4 times 0, because that was the lower one there. So 4 times 0 is 0. 0 plus 9 is 9. So my new u limit is 9. To figure out the upper limit, I'm going to take 9 plus 4 times 18. So 4 times 18 is 72, plus 9 is 81. So there are the new u limits. And if I plug in what I know, well, I know down here, this is going to be the square root of u, and we know how to work with that. I still got the x on top. The dx is 1/4 du. Since this is a constant, I can put it out front and then put du here. Uh-oh, there's a problem. My answer is supposed to be in terms of nothing but u. I still have an x that didn't go away. So how do I fix that? Well, there's another little trick. Up here, you know what u equals in terms of x. Well, why don't we find out what x equals in terms of u? So let's take this u equals 9 plus 4x. Let's solve for u. We can do that. That's it. Okay. So we're going to subtract 9 from both sides. All right. So 4x equals u minus 9. And then all we got to do is divide by 4. So couple ways that you can write this up. You can call this 1/4 u minus 9/4. You can call this u minus 9/4. Sorry, you can't see that. Or the way that I would do it, and you'll understand why here in a second, is I would pull out that GCF of 1/4 and have it 1/4 times u minus 9. This would be the guy I'm going to use to replace x, because all these are the same thing. We now know what x equals, and I can replace it and have nothing but u's. So using this 1/4 parenthesis u minus 9 parenthesis and replacing x, since this is a constant, I'm going to put it out front. So that's going to be 1/4 times 1/4, which is 1/16. Still from 9 to 81. The u minus 9 is going to go where the x is. All over the square root of u du. This is what they're after. Okay? So just a little bit of substitution. That's what we were doing throughout this whole thing, substituting in. See how this is in nothing but u's. Do not stop with an x in it. You need to take it to nothing but u's. Can be nothing else. And there you go. All right, number 11. Kind of the same idea, but this time it says use u substitution if you're going to evaluate the indefinite integral. What will u be in your substitution? Do not evaluate. So we don't want to change this around like what we did in number 10. We just want to know, what would you choose u to be? That's it. What would your u be? So looking at this, my gut again would be to make u equal 1 plus cosine t, the piece under the radical. And I know that is correct, because if I take the du of this, if I take the derivative, I'm going to get, well, the derivative of cosine. Again, I always double check because it's the signs. Signs I don't want to get wrong. The derivative of cosine is negative sine. See, that's why I check. I was about to say positive sign. Is negative sine t dt. And if you notice, this sign will cancel with that sign. So that's a good thing. These signs will eventually cancel out, because dt will be equal to a negative 1 over sine t du. See, and if I take sine t times 1 over sine t, they cancel each other out. And the negative would end up being in front. So you'd really just have a negative integral square root of u du. So that's how I know this is a good substitution. Let u equal 1 plus cosine t. It works out. Because again, in the end, it would look like this once completely substituted in. And that's easy to take the integral of. But again, we just needed to know what u was. All right, almost there, almost done. Number 12. So we want you to evaluate this indefinite integral this time. So let's find the antiderivative family. So again, in order to do this one, we're going to have to do some u substitution. So I'm going to let u equal what's under the radical. If you haven't noticed, that's kind of if you ever have a radical in your integral, that's usually your u usually ends up being what's under the radical. And if I take the derivative of this, du is going to equal negative 2x dx. And if I get dx by itself, I find out that we have 1 over negative 2x du. So let's plug in what we know. So integral x, this becomes square root of u. I made that way too big. And then the dx is equal to 1 over 2 x, sorry, negative 1 over 2, or the negative can be down in the bottom, it doesn't matter, x du. So there's some cleanup that we can do, because we can't evaluate this with two different variables. Well, the good thing is, what's going to happen to my x's? This one's in the numerator, this one's in the denominator. They cancel. Perfect. That leaves me with negative 1/2. Well, negative 1/2 is a constant. I can shove that out front. So the x's is gone. The negative 1/2 moved to the front. All that I have left in here is square root of u du. Oh, that's kind of a lot like what we were looking at in number 11 a moment ago. Another way to look at this is negative 1/2 integral of u to the 1/2 du. So this is just the power rule. So we're going to have, in the end, negative 1/2 times, well, remember the power rule, 1 over n plus 1, x to the n plus 1. Okay. Well, our n is a half, so 1/2 plus 1 is 3/2. But remember, we just talked about this. 1 divided by a fraction, just flip it. So 3/2 flipped is 2/3. And that's not an x, Mr. Armstrong, that's a u. We get u to the 3/2. And then we're going to plus c. Well, we can do some cleanup because we can multiply my two fractions and we know what u is. So we got to go back and replace it back to x. So negative 1/2 times 2/3 gives us negative 1/3. U is 5 minus x squared. And the power of 3/2 plus c. If you have me for class or some other lucky professor, this might be a problem that you have to turn in to me. Okay. So if you have me for class, sure, you're going to do this and turn this problem in to me. Okay. There we go. There's number 12. Number 13, you can see that the last part of this test, once you get past number 7, the second half of this test goes pretty quick. Like 1 through 7 are all about those Riemann sums and everything like that. So if you have me for class or some other lucky professor, this could be a problem that you could turn into us. So we're taking the integral from pi over 4 to 3 pi over 4 of, and this should have been distributed through. This shouldn't have been separated like that. So this is going to be 7 secant squared t plus 3 secant t tangent t dt. That secant should have been distributed through there. So that's just something we'll have to go back and fix. No worries. So it really should look like this. 7 secant squared t plus 3 secant t tangent t dt. So we want you to evaluate the integral. Well, that's not bad because if you looked at your list of shortcuts, secant squared is on there. Where's my shortcuts? There they are. Shortcuts. Secant squared is tangent x. Cool. And you also, if you look at your shortcuts, secant t tangent t is on there. Secant tangent right there. It's secant. Cool. So real quick, just showing you some things. If I apply my integral properties, I can move the 7 out front. And it's from pi over 4 to 3 pi over 4 of secant squared t dt plus move the 3 out front because it's a constant, pi over 4 to 3 pi over 4 of secant t tangent t dt. That's what it really looks like with properties involved. And then we already know what's going on here. We already know that secant squared, the antiderivative is tangent t. So this is 7 tangent t plus 3. We already know that secant t tangent t is secant t. And we don't put a plus c because we are actually have a definite integral. So we're going to evaluate. And this is why I have my little trig table chart. So I can look this information up. So all we got to do is evaluate now. So we're going to have plugging into 3 pi over 4, 7 tangent 3 pi over 4. And I know these directions didn't say anything about rounding or anything, but I'm pretty sure that this is going to be an exact answer. I don't think they want you to round on this. So just so you know. So 7 tangent 3 pi over 4 plus 3 secant 3 pi over 4. And then we're going to subtract off 7 tangent pi over 4 plus 3 secant pi over 4. So we're going to need to go to our trig table and do some substituting in. So we're going to have 7 times tangent of 3 pi over 4. So here's 3 pi over 4. Tangent is -1. So that's 7 times a -1. And then we got plus 3 times secant of 3 pi over 4. So secant of 3 pi over 4 is negative square root of 2. So that's 3 times a negative square root of 2 minus 7 times tangent of pi over 4. So we need pi over 4. Pi over 4, tangent is 1. So that's 7 times 1 plus 3 times secant pi over 4. Secant is square root of 2. So that's 3 times the square root of 2. So going back to what I know, I really don't need these anymore. All right. So tangent 3 pi over 4 was at -1. Secant 3 pi over 4 was at negative square root of 2. Tangent pi over 4 was 1. Secant pi over 4 was the square root of 2. So here's what we know. So cleaning up a little bit, 7 times -1, -7. This will give us a -3 square root of 2. In here, this is going to change all the signs to the opposites. So this will again be a -7. And this right here will again be a -3 square root of 2. So combine like terms. -7, -7 is -14. -3 square root of 2, -3 square root of 2 is a -6 square root of 2. And there it is evaluated. Okay. Number 14. This is all about properties of integrals. And I want to know if this is true or false. Okay. So is it true that if f is continuous on a to b, which is good, that if I have x times f of x in an integral, I can pull the x out? Is that true or false? Well, that is false. The reason it is false because these are two functions being multiplied together. This is a linear function. This is whatever f of x is. So you can't just pull the x in front. That's not a constant. That's an actual variable. So only constants can be pulled in front. Numbers. This is a variable. Doesn't work like that. All right. So this one, f of x, or f is continuous on a to b, and we know f of x is greater than 0, so that's good. So we don't have to worry about complex under here. So the question is, can we do that? Can I pull the integral inside? And again, the answer is no. You can't do this. This is a composition of functions. It doesn't work like that. Okay? We can't just pull in our integral. All right? So B, that one is also false. Doesn't work like that. We would have to do like a U substitution on this, maybe. Okay? Because if that was true, I would have been able to do it on some of these that we had up here. And we know that we couldn't. All right, last but not least, if f prime is continuous, so if f prime is continuous, that means f is continuous. So that's good. Then the integral from 8 to 6, we know that this is the derivative. Is this true? That this is f of 8 minus f of 6. Is that true? So the idea here is this is the second part of the fundamental theorem of calculus. Can we get away with that? And the answer is yes. This is true. Because remember, when you take the integral of this, you get the original function, f, and you plug these two numbers into f. So this is true. Because again, it's the second part of the fundamental theorem of calculus. Okay? So it works. It's good. So we got false, false, true. All right, last but not least, number 15, and we're done. Yay! Number 15. So depending on your professor, you're probably going to sketch a screenshot here. If you are one of my students, or maybe if you ask your professor, I'm going to ask my students to take a screenshot from Desmos or wherever they get it. So we got this oil tank, or this oil storage tank that erupts at time 0 and leaks from the tank at a rate of this. So in the end, we want to complete part A. So I want a picture of this. What does this look like? And then we want to know how much oil leaks out during the first hour. Round it to the nearest liter. So that's like the whole number. Okay. So we're concerned about the first hour from 0 to 1. Okay. But be careful. This is all about liters per minute. So maybe instead of thinking about this in hours from 0 to 1, what if we think about it from 0 to 60? Because it's easier to change this than it is to change into our equation. Change what we're evaluating from. So note, in this problem, time is in minutes, but we want to integrate from 0 to 1 hour. So really watch those labels. What we really want to do, let's change this hour into minutes so that everything lines up. 0 to 60 minutes. That would be better. Okay. So when I go to make a screenshot, I want to make sure my screenshot shows me this information from 0 to 60 on the x-axis, and then I see my picture. So I'm going to go out here to Desmos. I'm going to type in my equation, and my equation. Actually, let's write up what we're really trying to do here. So what we're really trying to do is we're trying to integrate from 0 to 60 of our function, the rate, which is 75 e to the negative 0.02 t dt. So this is what part B is after. We want to integrate this. And part A just wants a picture of this. So all we're going to do is we're going to plug in this equation, 75 e to the negative 0.02 t, and get a picture from 0 to 60. So 75, f of x equals 75 e to the negative 0.02 x. All right. So obviously we're not seeing anything on here, but it is graphed, I assure you. We just have to zoom out. Okay. So I'm going to mess with my little gear setting right here. Or, if you want, you can, scroll up, scroll down. Hey, there's our function, right? So that's not a bad shot, but I'm going to mess with it a little bit more. So I'm going to make my x-axis go from -2. And actually, I'll make it go from -10 all the way up to, we'll say 80, and we'll count by tens. My y-axis, so it looks like I want to be in here around 0. So let's make the top of my y-axis 80. And then down here, we'll go to -10. And we'll count by tens. So there's a great picture. I can see 0. I can see 60. So all I got to do then is I can go up here to share, and I can print my graph, which will save it as a PDF. Or if you need to sketch it, you can sketch your picture from there. So this is exam 4 review. Exercise 15A. And this is, I'm going to call this Plaza because I do have one for my class. And I'm going to go ahead and save my graph on here. Let's get a new name for it. Exam 4, exercise 15, or exam 4 review. Say review. exercise 15A, call this Plaza. And there we go. So we've got everything we need for part A. That's what part A looks like. That's what we want. Okay. So I don't need Desmos anymore. So we've got our part A. Remember, I called that file exam for review. Exercise 15A Plaza. So part B, all we got to do now is evaluate. Well, in order to evaluate this, you got to use U substitution. So we're going to let I'm going to let it equal this power here. Because if I can get e to the power, or like e to the x, that's easy to integrate. So negative, I don't know why I'm trying to write it as a power in here. So u equals negative 0.02 t. So du is equal to negative 0.02 dx. So dx is 1 over negative 0.02, or you can put the negative 1 in the top, du. So let's do some replacing. Since this is a constant, I'm going to move it out front. And since this is a constant, I'm going to move it out front. So in front, I'll have 75 over negative 0.02. Because 75 times 1 is 75, and then it stays over that number. We're going from 0. Ooh, we are not going from 0 to 60 anymore because we are doing a u substitution. So my new u's are negative 0.02 times 0 and negative 0.02 times 60. So let's figure out what these u's are. So anything times 0 is 0. Cool. So 60 times negative 0.2 is negative 1.2. Okay. And then we have e to the u du. Okay. Now, here's the thing. Usually this number should be the largest one, but it's not. So what that means is when we get our final answer, we need to take the opposite of this, because whenever your integral, your A's and B's are switched, where this is the B and that's the A, because the A should be the smallest and the B should be the largest, you have to take the opposite of the integral. Okay? You have to take the opposite of it. So keep that in mind. In the end, another little note. Take the opposite of the answer. In the end. Okay. So the integral of e to the u. So we'll have 75 over negative 0.02. Integral of e to the u is e to the u. And we're going to evaluate that from 0 to negative 1.2. There we go. So that's what we want to figure out. So we got 75 all over negative 0.02 e to the negative 1.2 minus 75 all over negative 0.02 e to the 0. So we just go to our calculator I'm gonna put this in. So I'm gonna definitely use my fraction keys, and I'm not showing this because you guys can go into your calculator and evaluate this. E to the negative 1.2. All right. And then I'm subtracting for negative 0.02. E to the 0. And my calculator says that we have a, make sure I have my signs right. Yep. Positive 2,620.521,705. But remember, we need the opposite of this answer. So that's negative 2,620.521,705. And they said to the nearest liter, which would be the whole number. So that would be negative 2,621 liters. And that makes sense because this is asking us about how much oil has leaked out during the first hour. So this tanker has lost 2,621 liters in the first hour. That makes sense. That's why it's, excuse me, negative, because it is losing oil. And that, my friends, is the exam for review. Thanks for stopping by.